Our lives are governed by the steady tick-tock of the clock. Seconds, minutes, hours, they march forward with what feels like an unwavering, universal rhythm. But is that feeling an illusion? Have you ever stopped to truly wonder if time is the same for everyone? Everywhere. Is your now identical to the now of someone on the other side of the planet, or even just a few floors above you? We often think of time as a constant river, flowing at the same steady pace for all of us. It's a comforting thought, suggesting a shared, objective reality where 1 second for you is 1 second for me, no matter what. But what if that river has currents and eddies? What if its flow can be bent and stretched? The truth as revealed by modern physics is far stranger. For instance, standing on the ground makes your time pass a tiny bit slower than for someone flying high above in an airplane. The person in the sky is literally aging a fraction of a second faster than the person on the ground. It sounds like science fiction, but it is a fundamental truth about our universe, a core prediction of Albert Einstein's theory of general relativity. The culprit is gravity. The very force that keeps our feet planted on Earth doesn't just pull on objects, it warps the fabric of reality itself, subtly slowing the passage of time. This isn't a wild theory or a philosophical musing, it's a measurable, physical reality, confirmed by countless experiments with astonishingly precise instruments. And you don't need a PhD to grasp the concept. We will explore it with simple ideas and clear examples, no complicated math required. To understand this, imagine two perfectly identical, extremely precise atomic clocks, the most accurate timekeeping devices ever created by humanity. Now let's conduct a thought experiment. Place one clock in the basement of a New York skyscraper, and the other on its top-floor observation deck. You synchronize them perfectly, and let them tick away. After exactly 1 year passes, you bring them back together to compare them. You would find that the basement clock is a little behind, by about 90 billionths of a second. It's an infinitesimal amount, but it's real. The reason is simple. The basement clock is closer to Earth's center of mass. Here, gravity is slightly stronger and therefore, time itself runs just a little bit slower. So when we say gravity slows time, we mean the flow of time isn't absolute. It's not a universal constant ticking away at the same rate for everyone. Instead, time is relative. Its pace depends on your position within a gravitational field. Your personal experience of time is unique to your location. The rule is straightforward. The closer you are to a massive object, the stronger the gravitational pull and the slower time passes for you compared to an observer farther away. This fascinating and mind-bending effect has a name: gravitational time dilation. Dilation simply means stretching or slowing down. On Earth, the effect is minuscule, and you never notice it because every process, from your heartbeat to the chemical reactions in your brain, slows down together. From your perspective, everything always feels perfectly normal. To connect gravity and time, use a helpful analogy. Einstein reimagined gravity as mass and energy warping spacetime. Massive objects create curves or dips in that fabric. Those curves dictate how objects move. The Earth isn't pulling you down, spacetime is bent, and you follow its straightest path. Time is woven into that fabric. When gravity bends space, it also bends time. Picture a large, flat trampoline, spacetime. A heavy bowling ball creates a deep curve, like a massive planet or star. Roll a marble nearby, it curves inward, what we perceive as gravity. This also visualizes time. Deeper in the well, progress is slower. Time passes slower. Think of time as a river. Far from masses, it flows steadily. Near a massive object, it's like a whirlpool. Currents become complex and slower. Closer to the center, motion is slower. Farther away, faster. This is a powerful way to picture gravitational time dilation. Warped time affects light too. Climbing out costs energy, stretching its wavelength. Its color shifts toward red. Gravitational redshift, observed by scientists. The idea that gravity can slow down time isn't just a mind-bending theory, it's a physical reality that has been rigorously tested with astonishing precision. One of the earliest confirmations was the Pound-Rebka experiment. By sending gamma rays up a 22.5-meter tower, scientists measured a tiny but definite change in their frequency. As the gamma rays climbed against gravity, they lost a minuscule amount of energy, causing their frequency to decrease. This is a form of gravitational redshift. When they reversed the setup, sending the rays downward, the opposite occurred, a blue shift. The results perfectly matched Einstein's predictions. The implication is clear. Time itself runs slower at the bottom of the tower than it does at the top. This effect is so fundamental that it even exists between your head and your feet. The difference is infinitesimal, but it is real. In fact, if you wore a watch on your wrist for a year, it would run a few nanoseconds faster than a clock left on the floor, simply because it's in a slightly weaker gravitational field. To measure these tiny discrepancies, we need incredibly precise instruments. Modern atomic clocks are so stable, they wouldn't lose or gain a second in billions of years. In one experiment, when two such clocks were placed just 33 centimeters apart vertically, the upper clock was measured running faster than the lower one. Exactly as predicted. There's no doubt, gravity bends time. And this isn't just a laboratory curiosity. If you've ever used GPS, you've relied on our understanding of gravitational time dilation to find your way. The Global Positioning System consists of about 31 satellites orbiting Earth at an altitude of roughly 2,200 kilometers, or 12,550 miles. Your phone's receiver measures the precise travel time of signals from multiple satellites to triangulate your exact position on the globe. For this to work, the timing must be synchronized to within nanoseconds. Even a tiny error of a few billionths of a second translates into meters of position error on the ground. Because the satellites are in a much weaker gravitational field than we are, their onboard atomic clocks run faster than ours by about 45 microseconds every day. At the same time, their high orbital speed causes their clocks to slow down due to special relativity by about 7 microseconds per day. The net effect is that the satellite clocks gain about 38 microseconds relative to ground-based clocks every single day. If this discrepancy were left uncorrected, your GPS location would accumulate an error of about 10 kilometers, or 6 miles, after just one day. To prevent this, engineers build the satellite clocks to run slightly slower in the factory, and the system's software makes continuous adjustments. So every time you see that blue dot, you can thank Einstein. To grasp the true power of gravity over time, let's start with a famous thought experiment. Imagine two identical twins, Anna and Ben, each with a perfectly synchronized, high-precision clock. On their 20th birthday, Anna, an intrepid astronaut, embarks on a mission to a distant star, traveling at a speed incredibly close to that of light. Ben remains on Earth. From Ben's perspective on Earth, the journey takes a long time. He lives his life, and 40 years pass. He is now 60 years old. But for Anna, hurtling through space at near-light speed, time itself slows dramatically. For her, only about 10 years have passed. When she returns, she is 30. This is the famous twin paradox, a classic illustration of velocity-time dilation from special relativity. The faster you move through space, the slower you move through time, but velocity isn't the only thing that can warp our temporal reality. Gravity does it too. Now, let's change the scenario. Instead of moving fast, we place Anna near a supermassive black hole, where gravity is incomprehensibly strong. She orbits safely, spending what feels like just 5 years in this deep gravitational well. When she returns to Earth, she finds that centuries have passed. Ben is long gone, entire generations have come and gone, and the world she knew is ancient history. The stronger the gravity, the more time slows down. This isn't just theoretical. A clock near our sun ticks a tiny fraction slower than one in deep space. This effect applies to all processes, chemical, biological, and mechanical, including aging itself. The ultimate expression of this is a black hole. Imagine watching an unlucky astronaut, David, fall toward its event horizon, the point of no return. From your safe vantage point, he appears to slow to an agonizing crawl. Any signals he sends back, like flashes of light, become less frequent and stretch to longer, redder wavelengths. As he approaches the horizon, he appears to freeze in time, his image fading into nothingness over an eternity. You will never see him cross. But from David's perspective, nothing unusual happens to his sense of time. His own watch ticks along normally, and he crosses the event horizon in a finite, and likely very brief amount of time. Two starkly different realities coexist. One of the most striking and mind-bending predictions of general relativity. Black holes aren't the only places like this. Neutron stars also host extreme gravity. These are the collapsed cores of massive stars, packing more mass than our sun, into a sphere only about 20 kilometers, or 12 miles wide. The gravity is so ferocious that a clock on a neutron star's surface would tick about 30% slower than one far away in space. Because we can observe them, these incredible objects serve as natural laboratories, allowing us to test the limits of gravity and the nature of time itself. From the subtle differences in our own homes, to the mind-altering edges of black holes, gravity is the silent conductor of spacetime's rhythm. Time is flexible, a profound shift in human thought. It underpins cosmology, lensing, the Big Bang, and our models of the universe. It powers technologies like GPS and guides ever more precise engineering. Think of the universe's tempo. Near mass, the rhythm slows. The music of spacetime. Locally you don't notice, but across different regions the tempo differs, from tiny differences across a building to extreme bends near black holes. It's the same principle. Einstein's ideas run quietly inside your phone. When you climb stairs, you move a bit faster into the future than the floor below. Keep your curiosity alive. The universe is stranger, richer, and more beautiful than we imagine. Time isn't just a clock on a wall, it's part of the grand cosmic dance, and we are fortunate to have a front row seat.